LB 2.2. Today we're going to start by talking about a simple question. Imagine you have these three letters, A, B, C, and the question was, how many ways could you arrange these letters? Well, clearly you could just kind of power through, right? A, C, B, B, A, C, and so on. Or, if you're really good at last chapter, you would say, well, there are three of them, so I'm going to do 3 factorial, because it should be 3 times 2 times 1, which is 6. So there are 6 ways that this can happen. And hopefully at this point, that's what you can do. Now the question becomes, what if one of the letters was the same, like A, B, B? Now how many ways can you arrange these? Because these B's are the same thing. So I could write B, A, B, or B, B, A. And notice how there's no other way to do this, right? Because these B's are identical, so switching these wouldn't mean anything. So I can see that there are 3 of them. But the real question is, how do these connect? How do you get from here to here? Well, what you have to do is basically take that 6 and you divide it by 2 factorial. So what you're saying is that's your total possibilities, and you're dividing it by 2 factorial because that's all the ways the B's can move around. The ways B can move around. Because we call this a repeated element. And that's what we're doing today. So if you look at this thing, it says count the number of words, so don't worry about they're actually a word, that can be formed using the letters in each word. So dragonfly, notice how each letter is unique, so that's just 9 factorial, which is 362,880. But now we have butterfly. So notice how there are 9 letters total, so that's where you start. But now you're going to divide it by everything that has a multiple or an extra letter. So there are 2 T's, and that's it. So you divide it by 2 factorial, which becomes 181,440. Notice how it's exactly half of these, which makes sense because these 2 T's will get counted too many times if I didn't divide it here. So before I do this last one, you'll notice the formula is simply this. N factorial over A factorial times B factorial times C factorial, dot, dot, dot. These are your repeated elements, and then N are your total elements. And again, this is your formula for repeated elements of what to do. So repeated elements formula. That's definitely one you want to put a box around. Okay, next example. Oh, sorry, we didn't do C. Let's go back to that. So there are 9 letters, so 9 factorial. I notice there are 3 B's, so 3 factorial, and 3 E's, so that's 3 factorial. I reduce that, that would be 10,080, and we're done. Next example. In how many ways can 5 people sit around a circular table? So that's kind of tricky, because now we have a circle, and then there are going to be 5 people, A, B, C, D, and E. And the question is, well, how many ways can these people sit around this table? Now, a lot of people would just want to say, well, wouldn't it just be 5 factorial, right? Because that's what you would do if they were like sitting on a bench, for example. If it was A, B, C, D, E, you just say 5, 4, 3, 2, 1. Unfortunately, it's not that simple. That's because if I were to rotate everybody, like let's say I rotate it like this, to make it easier, I'll even put a position here. Let's say this is position 1, 2, 3, 4, 5. If I grab everybody and I rotate it like this, is that really a new seating arrangement? Even though everyone's sitting in a technical new spot, if this is you and your friends, you're all sitting by the same person. And notice how I can keep doing that with this particular arrangement. I can move it here. I can move it over here. Pretty much no matter how I move these positions, you're going to end up sitting by the exact same people. So that's a problem. We got to figure out how to do that. So there are a couple ways you can do this. For this particular one, you start with 5 factorial, meaning you assume it was, quote, normal. So essentially like a line, even though we know that's wrong. And then we're going to divide it by the number of spots there are, which is 5, because that's how many ways I can rotate everybody here. So imagine I rotate it. I can rotate it 1. Grab one more time. I can rotate it 1, 2, 3, 4, and 5. So I can rotate it 5 times and I'll get the exact same arrangement, which means I should divide the total by 5 because everything will get counted 5 too many times. That would reduce to 5 times 4 factorial over 5, cross that out. And 4 factorial is simply 24. So that's one way to do it. So some people do n factorial over n as your circular permutation formula. So circular permutation. Now there's another way to do it. Some people do it like this. Imagine a circle. What they do is instead of thinking of it as a rotation, they say, one person, I'm going to make sure you don't move. Like let's say I tell this person right here, you don't move. Everyone else, we want to rotate. So I'm going to rotate everyone else. Actually, I'm going to have to grab them physically. Everyone else, so like B, C, D, and E. And rotate around this one person. Because that would mean that's going to guarantee a new seating arrangement because this person is not moving. So that kind of avoids that whole issue. So that's another way to think about it. And that's actually much easier because now I can just think of these as slots and just write 4, 3, 2, 1, which is clearly 4 factorial, which would be 24. So another formula you can write is n minus 1 factorial, which is essentially saying you're going to fix one person. That's how you're subtracting 1. Okay, let's go to our next example. So now we're going to talk about combination. So everything we've done so far is called permutation. So if you look at this thing, notice how it says permutation. Permutation is when the order matters. So you notice that for all these letters, the ordering matters, and that's what we're counting. So make sure to make a note here. Permutation, order matters. But now we're doing combination. In combination, order does not matter. Doesn't matter. And I'll show you the question that kind of models this. A 3-person committee is needed. How many committees can be formed from the 8 people on the board of supervisors? So there are 8 people total, and we're going to pick 3 of them. So order wouldn't matter here because it doesn't matter how you get picked in the committee. You're just in the committee or you're not. Right? So it doesn't matter if you're picked first or third. If you're in the committee, that means you're a part of it. That's what it means, and order has no meaning. Now I'm going to give you the formula for this. Instead of NPR, it's NCR. So that's why you have to do the permutation formula, because you're going to see the the link here. Notice how this part is identical to the permutation formula, except now we have an extra r factorial on the bottom. So it's critical to understand the permutation formula to understand why this is going to work. The permutation formula was this, n factorial over n minus r factorial. So again, notice how they are identical. N is still your total, and r is still the amount you're choosing. The difference is, in this one, order does not matter. Now when you're using these, you have to remember that there are going to be stipulations. The main thing to know is this. The elements can't repeat, meaning you can't use a person more than one time. So these questions, or this formula in general, they're really good with people. So good for people problems. For this formula, remember permutation, order matters. For this one, order doesn't matter. Now the reason you have this thing here is because that's going to divide out the repeats. That's what it means when order won't matter. You have to get rid of the extras here. So for this one, you're going to write 8C3. That's 8 factorial over 8 minus 3 factorial times 3 factorial, 8 factorial over 5 factorial times 3 factorial, and I pretty much got it. Notice how the 5 factorials cancel. 3 factorial is 6. So the answer is 56. So we can do that by hand. That's pretty nice. Now here's the last example. So it's a poker question. It says you dealt 5 cards from a standard 52 card deck. The order in which you dealt the cards, or the order doesn't matter. So that's classic for a card question. So combination is great for cards. So I'm going to write a note here. Combination because in cards, typically order doesn't matter. How many different 5-card poker hands are possible? So there are 52 possible cards. C, because order doesn't matter. And there's a 5-card hand, so 52C5. 52 factorial over 47 factorial times 5 factorial. Okay, this is going to be a massive number, so we're going to need our calculator. So let's go to our calculator. For factorial, well, first let's get the fraction. 52 factorial is going to be right here, shift 9, and there it is. And then we're going to put 47, shift 9, times 5, shift 9. There it is. So that's how many possible poker hands there are. And we are done.